Nobody wants to get lost. We want to know where we are and where we came from. We want to know what this is all about. This gives us a sense of control. This gives us context. Most importantly, it gives us direction. Basically, people want to have a big picture view of whatever they are about to study. However, in our present pedagogy, talking about the history of the subject and the family tree of that subject are considered a waste of time. It's like parents saying their children, why do you want to know how you were born and who are in an extensive family? Isn't it enough that I feed you, clothe you, and shelter you, and educate you? Such rhetoric is good and valid, but over time, the child will miss his roots and consequently feel emptiness and become directionless. That's an extreme, but nonetheless, he will not feel an attachment or a sense of belonging to the family. So before we move further in statistics, I will first introduce you with the family tree, and then I will tell you the history of statistics. Both are very interrelated, obviously. Having such a narrative in our minds as we study this complex subject help us know our directions. We know where it's coming from and where it's taking us. You can follow the diagram below as this exposition is based on it. So level 0 of statistics is the foundation. It's like the roots of a tree or the foundation of a building. It is the data collection and organization part. Without this, statistics cannot occur. The first part is tallying or counting. It's the most primitive form of data collection. I think you remember in some movies where the prisoners count how many days they have been in jail by marking the walls with 4 straight lines and then crossing them to indicate the 5th day, and then again making marks of straight lines. Then when the 4th is reached, it is crossed. In this way, that would mean 10 days in jail. That's basically what tally is. So this process leads to the quantification of discrete observations. The main objective is to get the raw data of high quality. Nowadays, we might not have to do the exact tallying. We just put a number. For example, when the government censor board comes to us and say how many people live here, we give them a number and that goes into this raw data. The second part is the organization, where this raw data is grouped, cleaned, and structured into formats that is suitable for future analysis. The focus is data integrity and manageability, and the organization takes form of tables, databases, arrays, and we clean the missing values. So this is the first layer of the hierarchy or family tree of statistics. This leads to the first branch called descriptive statistics. As the name description suggests, in this branch we are trying to find out what the data is saying. So the purpose is to summarize, organize, simplify the main features of collected data sets. It can be just a sample or the entire population. In this branch, there are 3 sub-branches. The first one is the measure of central tendencies. Here we define the typical or central value of the data. The various outputs or measures used are the mean, median, or mode. Then in this branch, we also want to know the measures of variability. We want to know how spread out or dispersed the data points are, and that's called range, variance, and standard deviations. The third sub-branch is the graphical representation. They are visual tools to communicate the distribution of data clearly. They take the form of histograms, box plots, pie charts, bar graphs, and so on. For most of students and professionals, statistics is limited to this branch. Knowing this much of statistics takes not too much hard work because it's very intuitive, as we have discussed in the earlier section. Knowing this much is enough for us to navigate the various data figures that prop up in the news and the various books that we read. The truth is, we don't need more statistics than this, unless you are into research, either formally or informally. Next in the family tree is a very important component, which is the probability theory. It is the bridge that links branch 1 to branch 2 and 3. Probability is a mathematical language and concept. Statistics didn't come up with it. However, it cross-pollinated with statistics. Now we know why a certain child is very different in his features than his biological or legal parents. There must have been some other contributors. Putting this dark joke aside, probability theory allows us to transition from merely describing what we observe, descriptive statistics, to predicting what we do not know. It was indeed a necessary discretion or digression. Because of it, branch 2 and branch 3 were born. The role of probability theory is basically to quantify uncertainty and the likelihood of events, providing them a mathematical basis for generalizing from a sample to a population. It's like testing a few drops of a lake to determine whether it is good for drinking or not down the road. We couldn't be fully sure, and we have needed to assign some probability. Without the later, generalization would always hit a wall. It would either be true or false, and anything in between would be considered blasphemy. So that is the importance of probability. It's basically saying truth is not exactly black or white, and there is a gray area. This is how important this was in the evolution or history of statistics. Some of the tools are random variables probability, distributions, normal distribution, and the law of large numbers that I used. So out of this cross-pollination or consummation, inferential statistics was born. This second branch basically tells us what we can conclude from the data that we collected, organized, and described. This branch is used to make predictions and to test hypotheses about a much larger population of which data we collected belongs. Again, in this branch there are 3 sub-branches. The first one is estimation. Here we use sample data to estimate a population parameter. This is about terms like confidence interval, which basically tell the range of values that likely contain the true population mean. The next sub-branch is the hypothesis testing, where I use the data to formally test a claim or theory about a population. In order to do that, we use measures like the t-test, ANOVA, chi-square. As we discussed earlier, they are used to determine if there is a relationship between 2 data sets and if they occur out of chance or not. The third branch is regression analysis. Here we make an equation or a model that describes the relationship between the data sets to predict the future outcome. It can be either a simple or a multiple linear regression depending on the number of independent variables or data sets. Then out of statistics and that bridge of probability theory was born branch 3. It's the advanced modeling and data analytics, or the application of statistics. Its purpose is to use statistical and computational methods on large complex data sets to drive automated decision making and forecasting. This branch couldn't have existed if computers were not invented, because the amount of calculations required is astronomical. Artificial intelligence is a product of this branch. We talk about DNA testing as if it's so simple and as if it's only innovation from biology. But without this third branch, how would we ever correctly infer that the two DNAs match? We need serious predictive power based on correct statistical theories. The same goes with fingerprint matching. Then we look at the news and decry the weatherman for making a wrong prediction about the weather because he said it would rain and it did not rain on that day. All that is the fruit of this third branch. It consists of 4 sub-branches. The first one being data mining. Here we try to discover hidden patterns, anomalies, and correlation in massive historical data sets. The best example are the recommendations you get on Amazon for the products that you might be interested in, but still more powerful are the feeds that we receive. The algorithm basically data mines our history of browsing and the available content, then feeds us with what is the most probable thing we'll like to watch. Product developers and researchers are always on the lookout for new data in order to extract knowledge and get unexpected insights. Thus the word mining. The second sub-branch is a time series analysis. It's like regression that we discussed in the branch 2, but it involves much more variables and thus requires much more computation. The basic use is to make forecasts that are based on time, like the stock prices, weather, sales volume, and so on. The third sub-branch is the predictive model. Now this is the big brother of all. It uses the findings from data mining and the time series analysis to predict anything. Whenever you use your keypad in your mobile, you must have noticed that it suggests to you the word that you might be trying to type before you finish it. That's basically a product of data mining and predictive modeling. It's supercharged statistics, and you never knew it. In the news, when we read the projection of the economy and the rate of increase of GDP, or a potential recession or inflation, that's again a combination of time series analysis and predictive modeling. The fourth sub-branch is data science. It's like the sibling who makes peace with everybody and links everybody. It's basically the broad interdisciplinary field that applies all the above methods with computation tools and domain expertise. So you know the predictions and the probabilities. Now somebody has got to extract actionable knowledge from that to solve complex business and scientific problems. This is what this brother does. So now you know the family tree and the hierarchy of statistics. Let's look at the history of statistics, the key eras and figures or personalities that are associated. Unlike mathematics and English or even accounting, we have to say that statistics isn't old. So many things had to occur, especially the rise of probability theory, then later on the rise of computation. Still, statistics is not just 100 years old. We can divide the history of statistics into 5 eras. Again, you can refer to the diagram below. The first era is the 7th century and earlier, or what we have called the prehistoric period for statistics. A suitable name would be the early beginners. The key concept and purpose is that in this era, statistics was rooted in tallying and counting. It evolved into descriptive statistics used for administrative and government purposes, like censuses, record keeping for military and taxes. Even though term statistics come from the word status, or Latin for state. Gottfried Achenwall was the person who coined the term statistic in the mid 18th century. Then the second era began in the 17th century, and we can call it the rise of probability. Here, statistics shifted from a simple record keeping to understanding randomness and uncertainty. This mathematical foundation was crucial for the later development of inferential statistics. The key figures were Girolamo Cardano, Blaise Pascal, Pierre de Fermat, who solves problems related to games of chance. So this is our mysterious ancestor that we talked about earlier that resulted in this unique cross-pollination or consummation that resulted in branch 2 and 3. Then the third era of modern statistics, which we call the foundational era, started in the 19th century up till the early 20th century. In this era, statistics became a distinct, rigorous field, introducing concepts for measuring relationship and variability in large data sets. The key figures were Adolphe Quetelet, who applied statistics to social sciences and crimes, Francis Galton, who pioneered correlation and regression, Karl Pearson, who developed the Pearson correlation coefficient and chi-square test. So branch 2 was born. Began in the early 20th century. It's called the modern statistics and experimental design era. This era revolutionized how experiments were designed and analyzed. In short, you can say that this is the foundation of almost everything, because all the sciences are based on it. Curing a disease is no more an act of faith nowadays, but it's the result of this era, modern statistics. No science hypothesis becomes a theory unless it rejects the null hypothesis. No theory can be used unless a predictive model can be built around it. So you see where I'm going. Every modern amenities that we have that is reliable at least is possible, because after this era we could test hypotheses in ways that is universally acceptable. We don't have to say I think it is true. All you have to say is the p-value is 0.02 or 2%. Two scientists don't have to debate. All they have to do is redo the experiment and the statistical calculation. There is no need of opinions. It's all testable. So the key figure was Ronald A. Fisher, who is considered the father of modern statistics because he developed p-values that we just talked about, ANOVA, and various principles of experimental design on which modern society is based on. Finally, We reached the fifth era, which is the contemporary statistics era. It began in the mid 20th century and it's extending up till now. It's highly correlated with the third branch that we discussed earlier. The focus in this era is on computation, large-scale data modeling, called big data, and integration with computer science and machine learning or artificial intelligence. There is not a single figure here, but it's an anonymous group of statisticians and computer scientists developing complex algorithms and predictive models. I'm sure that you didn't understand many of the terms here, but that's not the objective at this point. The big picture view is not about understanding or even knowing the details. It's just to see the contour of the landscape. From this section, now you know who are the ancestors, descendants, brothers and sisters of statistics as a dynasty. Then you also know the various eras that built on each other for us to reach at this point where we can almost predict anything except earthquakes, big geopolitical disturbances, and a few more. Of course, there is still much more work for statistics to do. However, as a student of statistics, seeing it from this high vantage point will help you not to get lost and find direction in your studies and use of statistics.